Mm, okay, so hello everyone. Today we will see the COA formula sheet. Like each and every important formulas we will see each and every important formula. Okay, so you don't have to go here and there. Within this sheet only, you will find each and every important formula. So I welcome you all. And before getting started, let me introduce about myself. So my name is Deadlock. Okay, my name is Deadlock. You can call me Deadlock. I got All India Rank 150 in GATE Computer Science, and I am the alumni of IIT Bombay. Okay, I am alumni of IIT Bombay. So some little bit introduction about myself. Now we will see this each and every important formula. Okay, each and every important formula. So first of all, right? So the prerequisite of this session is you first complete the COA course, then you complete the COA short notes, which is taken by me, and then you come to this formula sheet. Okay, then you come to this formula sheet. So first complete the entire syllabus, then you do the COA short notes class, and then you come to the formula notes. so that each and everything will be more clear. Okay, each and everything will be more clear. Now, starting with the first point. So what the first point says, so if address bus has n bits, okay, address bus has n bits, so maximum addressable location will be 2 power n, right? So if this is your address bus, if this is the address bus and it has n bits, okay, so you know, right, that there is a decoder which selects the decoder have input n. So okay, if decoder have input n, it will give 2 power n outputs. Okay, so 2 power n are the different memory locations, right? Different memory locations. So this is the memory. Okay, this is the memory. So if address bus is n bits, how many maximum addressable location you can address? You can address 2 power n. Okay, so this will be 2 power n, 2 power n, right? Now, next point is 32-bit data bus. If you have 32-bit data bus, okay, if you have 32-bit data bus, what does it mean? CPU can transfer 32-bit at once, okay. If you have 32-bit data bus, okay, data bus you have, then CPU can transfer 32 bits at once. So if you have higher bits, okay, higher bit, then higher throughput, right? So it's like, for example, if you have now 64-bit data bus, okay, so 64-bit you can transfer, right? 64-bit you can transfer. So that's what it is written here, that higher width. If you have higher width, which means you have higher throughput. Okay, higher throughput. Now, next important formula is, so if you have, if in a question it is given, if a 32-bit architecture, okay, 32-bit architecture is given. So what does it mean? It means ALU is of 32 bits, okay, ALU is of 32 bits. Then if 32-bit architecture is given, ALU is 32-bit, memory data register, okay, so this is data register. Data register is 32 bit and word size of CPU is 32 bits. Okay, word size of CPU is 32 bits. So this is very important. Like some of the questions are there. Okay, in PYQs, it's like they are giving this, and we have to infer word size. Okay, we have to, most of the time we have to infer what is the word size if 32-bit architecture is given. So please take care this point. Please take care this point. Okay, so now we go chapter by chapter wise. We go chapter by chapter wise, and we will see each and every important formula. So starting with the first chapter, which is memory organization. So here, this is the first important formula, that what is the standard representation of main memory? What is the standard representation? How you can represent any main memory? Okay, how you can represent it? So so you have to represent like number of cells into one cell capacity. Okay, what you have to give, number of cells into one cell capacity, okay, into one cell capacity. So this is the representation of main memory. Okay, so see here one example I have given. So if you have byte addressable memory, okay, byte addressable memory, so this is the memory, how you can represent. So 256 KB means 256k locations you have, okay, into 1 byte. And here see 256k into 8 bits, right? 1 byte is equal to 8 bits. So please take care this. Here in one cell capacity, always you have to write bits, okay, always you have to give answer, or always you have to write bits. And number of cells will be 256k, right? 256k, so number of cells or number of locations, all are same, okay, all are same into one cell capacity. But please take care, you have to give in terms of bits, okay, in terms of bits you have to put here bits, right? Now next is, if memory required, okay, so if you required a cross b bits memory, so see I have given here. So if this is the memory representation and number of cells into one cell capacity. So similarly, if this memory is required and a chip available, okay, so you have available chip C cross D, and you have to make this memory, you have to make this memory. What you can do, if these are the chips available, what you can do, how many number of chips will be required? Simply you can multiply like this way, A cross B divided by C cross D, okay. And see here, each and everything will be in bits. So that's what I told here, that you have to give in terms of bits. Now please take care, if you do division, then you have to divide this term only, and you have to divide this term only, okay. Don't do here like this way, like this way, okay. Don't do in cross way, okay. So you have to divide this multiplied by, you have to divide this, okay. You have to only divide a by a divided by c. Okay, So now moving further. So now next point is, if memory is given word addressable. Okay, if memory is given word addressable and word size is not given. Memory is given as your memory is word addressable memory and word size is not given. Then consider one word size equal to word size of CPU. Okay, if it is not given, then you can consider one word size. Okay, one word size equal to word size of CPU. Got it? Now, next point. If you have total number of address, okay, if you have total number of address or total number of locations, right? So let's say you have 2 power n locations. How many address bit? How to find the address bit? So here we have seen this way. If you have n bits, then you can do 2 power n, right? But now I am asking reverse question. If I have 2 power n, then how you have to, then what is the n bits? What you are doing? You are taking log, right? You are taking log power 2, log base 2 into 2 power n, right? So that you will get n bits. So that's what written here. That address bit, how you can find the address bits. So bits you can find with the help of, you have to perform log base 2 with the total number of addresses. Okay, with the total number of addresses. Now, next point. Okay, now next point will be, these two are very important point. Okay, some PYQs are also there. So let one refresh period have X amount of read and write and Y amount of refresh. Okay, so if this is the refresh period, okay, let's say if this is the refresh period, okay, if this is the refresh period, what they are saying, X amount of read and write. Okay, so this is X amount of read and write and Y amount of refresh. Okay, Y amount of refresh. So what is given? What is the percentage of time refreshing will happen? Percentage of a refreshing will be y times refresh is happening, right? So y divided by total time, right? So this is x plus y. This is total. This is x plus y, which is total. So that's what written here. Y divided by x plus y into 100, right? Into 100. So that you will get answer in terms of percentage. Okay, answer in terms of percentage. Now, next point. So in one refresh operation, in one refresh operation, what happens? One entire rows of cells are refreshed. Okay, in one entire row refreshed. Okay, so one chip refresh time. What is the one chip refresh time? So one chip refresh time equal to total number of rows, right? Because one chip, so each chip have different rows. Okay, so and each and every row we have to refresh. So total number of rows into refresh operation time. Yes or no? So that will be the one chip refresh time. And if you have many chips, okay, so also all chips are refreshed parallelly. Okay, all chips are refreshed parallelly, because let's say if you have 5 chips, so each and every 5 chips refreshed parallelly. So one chip refresh time is same as n chip refresh time. Okay, one chip refresh time is same as n chip refresh time. Okay, so now proceeding further, what is the little Indian? Little Indian means start with little and or LSB. Okay, and what is the big Indian? Start with big and or MSB. Okay, yeah. So this is all about the important formulas in memory organization. Now we look important formulas in instruction and addressing modes. Okay, instructions and addressing modes. So this is the format of instruction. Okay, format. Okay, this is the format of instruction. Like you have opcode and operand. Okay, if you have opcode and operand, you have two things, opcode and operand. And if opcode is of n bits, okay, if opcode is of n bits, then number of unique operations CPU can perform will be is equal to maximum number of instruction is equals to 2 power n. Okay, so if this is n bits, okay, if this is n bits, opcode means it is an operation code. Okay, operation code. Opcode means operation code. So it tells how many different operations you can perform. Okay, how many different operations you can perform. So if this is n bits, okay, if this is 7 bits, how many different operations you can perform? Different operations will be 2 power n, right? 2 power n. So that's what written here. Okay, that's what written here. Now we will see important formulas of addressing modes. Okay, addressing modes, or each and every addressing mode. So what is the addressing mode? Addressing mode says the formula for EA. Okay, And what is EA? EA means effective address. Okay, effective address. And what is effective address? Effective address means address of operand. Okay, address of operand. Okay, so what the addressing mode will tell? What the addressing mode will tell? They will tell that where is the operand. Okay, what is the address of the operand? How you get the operand? Okay, how you get this operand? How you get this operand? Now we have different addressing modes, and all are important. All are very important in gate exam. Okay, first is immediate addressing. So immediate addressing stands move I1 hash 5. Okay, so it means that I1 we are directly giving 5. Okay, I1 directly giving 5. Okay, now next is direct addressing mode. So effective address will be address in instruction. So if you have this data, okay, if you have this move I1 comma 1000, what does it mean? So if you have 1000 here, okay, because this is the operand, so you go to the memory. Okay, you go to the memory, and then here you will get operand. Okay, here you will get operand. So that's what here written. Effective address will be address in instruction. So in the instruction itself, right, this is the instruction itself, you will get the address. Okay, now next is indirect addressing. So indirect addressing, what it is, what is the indirect addressing? So here effective address will be memory of address. Okay, let's say 1000 is given. Okay, what you have to do? First you have to go to the memory. At 1000 location. Here you will get address of operand. Okay, here you will get address of operand. Let's say our operand is here. Okay, let's say our operand is here. So here you will get the operand. Okay, here you will get the operand. So two times you have to go. Okay, two times needs to access memory. Okay, access memory. And here one time access. Okay, one time access. Okay. So now next is register addressing. Okay, register addressing means operand is present in the register, like move I1 comma I2. Okay, it's like simple. It is a very simple, like operand is present in the register. Okay, operand is present in the register. Now next is register indirect addressing. So register indirect addressing means effective address will be content of R2. So here, for example, move I1 comma R2. Okay, so this is for this example only. Okay, so it's like if you have R2 here. Okay, now if you go to that whatever is present in the R2. Okay, like some value will be present content of R2. Okay, so if you go to the that content of R2, let's say 1000. Okay, R2 will be 1000. So if you go to 1000 here in the memory, you will get operand. Okay, you will get operand. So that is register indirect. So one time needs to go. Okay, one time needs to access. Got it? Now we have these three addressing modes, like index addressing. What is addressing? What is the effective address? Effective address will be base address plus index register. Okay, base address plus index register. So whatever content is given in the index register plus base address. Okay, now what is the base or displacement addressing? So it is effective address will be base register. Okay, so here instead of index register, here we will using base register. Okay, base register plus offset. Base register plus offset. Now, in the relative addressing or PC relative, effective address will be PC register plus offset. Okay, PC register plus offset. So here, if you have index register, then index addressing, base register, then base addressing, PC, then PC relative. Okay, so the name is given with respect of which register we are using. Okay, with respect of which registers we are using. Now there is one mode which is auto increment and auto decrement. So it's used for doing plus plus and minus minus, right? Plus plus and minus minus. And now the last mode is implied or implicit addressing. So here operand is implicit. Okay, operand is implicit. So example here is I'm giving clear A. So what does it mean? So without implied. Okay, so each and operand will be implied. So we are not specifying things explicitly. Like here A means what you have to clear. You have to clear the accumulator. Okay, clear accumulator. Got it? So this is all about instruction and addressing modes, like all the important formulas. Okay. Now we'll see the next chapter. Next chapter is risk and sales. So there is not the important, there is no formula. Okay, there is no formula in this topic, but I have put here because many PYQs are there in this topic. And if you know this table, then you can easily solve each and every question. Okay, because they are the pretty straightforward. They are pretty much straightforward because none of the question they ask with the formulas in this particular topic. Okay, so what is risk versus risk? So risk means reduced reduced instruction set computer. Okay, and CISC means complex instruction set computer. Okay, now we see both the table. So risk means in the risk we are using simple instruction. In the CISC we are using complex instruction. Okay, then in the risk we are using fixed length instruction. In the CISC we are using variable length instruction. Okay, why we are doing it? Because its job is to save time. Okay, is to save time. And its job is to save memory. Okay, is to save memory. So if you want to see each and everything in a detail, please watch my lectures. Okay, in EPT course we have I have told each and everything in a very very much detail. Okay, and then next is here simple and a limited addressing mode is used. In the CISC we are using complex addressing modes. In the risk you have limited less number of instruction. In the CISC you have more number of instructions. Okay, then it's easy to implement using hardwire. It is difficult to implement using hardwired control unit. Okay, hardwire control unit. Now here one cycle per instruction and here multiple cycle per instruction. Okay, multiple cycle per instruction. Now here register to register arithmetic operation only. Here register to memory, memory to register arithmetic operations only. Okay, in the CISC. And the last point is here we are using more number of register, and here we are using less number of register. Less number of register. So here we have complex instruction, variable length instructions, and complex addressing modes, right? For to save memory. Okay, saves memory. They saves memory because we don't have to add very lengthy instructions, right? Very very lengthy instruction. In the complex instruction, if we add one complex instruction, then it can do many operations. Okay, and here in the risk, each and everything will be simple because we want things faster, right? Faster. So simple instruction, fixed line instruction, less number of instruction. Okay, and here hardwired control unit is used because it is easy to implement here. And see, look here, one cycle per instruction, and here per instruction multiple cycle. That's why it is slow. Okay, it is slow also. Slow. Okay, so this is the comparison of risk versus risk. Okay, now now we are moving in the next chapter, which is disk. Okay, disk. So in the disk, these are the important formulas. These are the important formula. First is disk capacity. So disk capacity is equal to 2 into number of platters. So 2 into number of platters, that will give number of surfaces into tags per surface into sector per tag into sector capacity. Okay, into sector capacity. So total number of surfaces, then tags per surface. Okay, then what is the how many sectors per tag? Okay, sectors per tag into sector capacity. Okay, into sector capacity. Now here next point is each surface have one read-at head, and at a time only one is active. Okay, so if this is your disk, okay, if this is the disk, maybe I can give you like this way. And this is the spindle which is rotating. This is your arm assembly. Okay, arm assembly. This is the arm assembly, and here you have different surfaces. Okay, so here each and every surface you have. So if this is called as platters, okay, these are called as three platters here in this diagram. And total how many surface? 2 into 6, right? So 1 2 3 4 5 6, like front and back, front and back, front and back. And each surface have read-at head. Okay, so this is the read-at head. This is the read-at head. Got it? So here what they are saying, each surface has one viewed head, and at a time only one is active. Okay, so at a time only one is active. Okay, only one is active. Now number of surfaces will be 2 into number of platers. Okay, 2 into number of platers. Now next point is sector of tag. Okay, so sector of tag is same as disk sector. Okay, disk sector which is same as sector of tag. Okay, sector of tag. Now sector is the smallest reducible unit. Okay, small sector is the smallest reducible unit of disk. It is the smallest reducible unit of the disk. Now, some formulas related to disk access time. Okay, disk access time. So disk access time will be seek time. Okay, seek time plus rotational latency plus one sector transfer time plus other delays. Okay, plus other delays. So seek time means which means you first come to under particular track. Okay, particular track. Then rotation latency means you come under particular sector. Okay, particular sector. Here seek time means time required to come to the particular tag. So that time is called as seek time, and time required to come under particular sector, that time is called as rotation latency plus one sector transfer time and plus other delays if take zero if nothing given in the question. Okay. So if nothing is given, take zero. Okay, take zero. Now what is the average rotation latency? Average rotation latency equal to, okay, average rotation latency is equals to rotation time divided by 2. Okay, rotation time divided by 2. So if you are given example, let's say 2000 rpm. Okay, 2000 rpm, which means 2000 evolution per minute. So in a 60-second 2000 evolution. Okay, what is the rotation time? So one evolution, what is the time? Okay, what is the time? That will be 60 divided by 2000. So this is the one rotation time. Okay, one evolution time or one rotation time. So that divided by 2 if you do, then you can get this particular quantity. Okay, average rotational latency. Now, what is the one sector transfer time? One sector transfer time will be same as rotation time divided by sectors per track. Okay, sectors per track, because in a one rotation, one entire track is transferred. Okay, one entire track is transferred. So one entire track is transferred, and in a each track, total number of sectors are there, right? Because if this is the track, so each track have different sectors. Okay, so what is one sector transfer time? In one rotation, let's say one entire tag transfer one tag. Okay, so what is the one sector? So let's say in one tag, let's say 60 sectors is given. Okay, example 60 sectors. Okay, so what is one sector time? What is one sector transfer time? So rotation time divided by sectors, right? So that's what it is, the formula. Okay, that's what it is written here. Now next is number of cylinders. Number of cylinder is same as number of tags per surface. Okay, number of tags per surface. Like how many total per surface. Okay, so if this is the per surface, how many tags you have, those will form cylinders. Right? So here let's say three tags are there. So three cylinders you are forming. Okay, three cylinders it will form. So that's why number of cylinder is same as number of tags per surface. Now these two are the again very important formulas, like sequentially stored. If sequentially stored n sector transfer time, what is the formula? Seek time plus rotation latency plus n sector you have to transfer that. So n into one sector transfer time. Okay, n into one sector transfer time. And if you have randomly, okay, now next is if you have stored you have stored randomly stored n sector. Okay, if you have stored randomly n sectors you have stored randomly, what is the transfer time? N into, okay, n into, so n times, because each things are randomly, right? Randomly, n into we have to do seek, we have to come to the particular tag, then we come to the particular sector, and then you transfer, right? Then you transfer. So this much time is needed. Okay, this much time is needed. Now proceeding further, so the next point is what is the disk addressing. So if this is the chs, okay, this is the chs. C means cylinder number, h means surface number, s means sector number. What is the sector number for given address? Okay, so if you have chs, what is the sector number for this address? So c into sectors per cylinder you do plus h into sectors per track you do plus s. Okay, plus s. So this is also again important formula. Okay, again important formula, because this comes in many questions. Okay, this comes in many questions. Now now let's say you are given some sector number. Okay, some sector number you are given. How to convert back to chs? Okay, back to chs. So this is the this formula converts chs to sector number. Okay, sector number. And that is also called as lba. Okay, that is called as lba. And here sector number like lba, which is given, how you can do chs. So these are the formulas you can, these are the formulas you can follow. But simple way to do is, let's say this is your nc and this is your nh. Okay, so what you do, you take the sector number. Okay, you take the sector number, you divide first of all by nc. Okay, you divide by nc. Now whatever quotient you get, okay, whatever quotient you get, okay, so here whatever quotient you get, okay, whatever quotient, that is your c. Okay, that is your c. Then whatever remainder you have, okay, whatever remainder you got, what you do, you again divide by nh. Okay, you divide by this quantity nh, sectors per tag. Then whatever quotient you are getting, that is your h, and whatever remainder is you are getting, that is your s. Okay, that is your s. So now if you look to this formula, that represents this same thing. Okay, same thing. So C equal to sector number divided by sectors per cylinder, H and S. You can follow. Okay, but always I am following this method, because if I follow this method, then I won't make a question wrong. Okay, I can easily solve. I can easily solve. Now one important now important thing, in the last thing which is important, that is disk. Okay, so this is not a formula anything, but it's a concept. But I put it, let's say, because it is important. Okay, so you have four algorithms, like scheduling algorithms. Okay, scheduling algorithm, like this scheduling algorithm. So scan, c scan, look, and c look. So what you do in the scan, if this is the direction, okay, if this is the direction, you go to this direction till end, and you serve all the requests. Okay, then you turn back, and then you serve all the requests till another end. Okay, till another end. And then again you change the direction. Okay, again you change the direction. So this is the scan means it goes till the end. Okay, scan means it goes till the end. Now if you see first of all look, okay, you see first of all look. Now if this is the direction, okay, so loop doesn't go till the end. Okay, doesn't go till the end. So here it goes until this request. Okay, because then there is no further request to handle. Then it turns its direction and it goes in this way, and again it not go till the end, and then again it will change it. Okay, again it will change it. So it goes till the request is present in one direction. Okay, so it won't go till the end, it goes till the request is present. Okay, till the request is present. Now now if you look c scan, okay, in the, if this is the direction, okay, so what the c scan do, c scan means circular scan. Okay, circular scan. So it performs the request only in this direction. So it performs in this red color, look into red color. So it performs in this way, then in this direction it won't perform, and then again in this direction it will perform. Okay, it will perform. And because it is scan, so it goes till the end. Okay, it goes till the end, it goes till the end. Now if you look c look, okay, if this is the direction, so again what the c look does, okay, same thing, see this. If this is the direction, this one, see the red color, it will serve here, then it won't serve here, and then again it will serve here. But what the look does, look won't go till the end. Okay, look won't go till the end, look won't go till the end. Got it? Yes or no? Got it? So now with that, the important formulas of disk is over. Okay. Now we'll see important formulas of floating point representation. Okay, floating point representation. So your any number floating, like float number. Okay, float number is represented in form s, e, and m. So s means sign. Okay, e means exponent, and m means mantissa. Okay, m means mantissa. Now the sign is plus or minus to 1 bit, at 1 bit plus or minus. So this is the exponent formula. Okay, see see actual exponent equal to stored exponent minus bias. Okay, minus bias. So here this is the stored exponent. Okay, we are what we are doing here, it is the stored exponent. So if you want to get actual exponent, right, you want to know what is the actual exponent. So how you can get, you can take the stored exponent minus bias. Okay, you do with the minus bias. And bias, if it is not given, can be calculated as 2 power k minus 1, where k is the number of exponent bits. So if here k bits, okay, if exponent is k bits, what is the bias formula? Bias will be 2 power k minus 1. Okay, bias will be 2 power k minus 1. Okay, so now proceeding further, uh, yeah, these are the value formula for explicit normalization. Explicit normalization means zero point 0.1. Okay, zero point 0.1, there is a fixed term, and this can be anything. Okay, this can be anything. And implicit normalization means 1 point m. Okay, 1 point m, 1 point m. So m means mentisa. Okay, m means mentisa. So this both the normalization wants your representation in this form. Okay, and this form, and then you can directly put this mentisa bits. Okay, directly put this mentisa bits here. Okay, mentisa bits here. So what is the explicit normalization? So it's minus 1 power s into 0 0.1. Okay, it should be 1 here, 1 here. Okay, 0 0.1 m into 2 power e minus bias. Okay, so see here actual exponent, right? Because we want the value, we want what is the value. So here actual exponent used, right? Actual exponent. And this is the implicit normalization, like minus 1 power s into 1 point m into 2 power e minus bias. Okay, into 2 power e minus bias. Now proceeding further directly with IEEE 754 representation, this is the very important. Okay, very important. Each and every gate question is coming in the latest years. Latest years, in the latest year, gate questions are coming. Okay, so and this 32 bit is very important. So single precision 32 bit. S is 1 bit, 8 bit for exponent, 23 bit for mantissa. The bias is fixed. Okay, bias is 2 power exponent minus 1. Okay, so 2 power 8 minus 1. Minus 1 you have to do. Okay, minus 1 you have to do, which means bias is 127 for single precision. For double precision, 64 bit. So 1 bit for sine, 11 bit for exponent, 52 bit for mantissa, and bias will be 1023. Okay, 1023. And note that by default, IEEE 754, this is the standard. It uses implicit normalization. Okay, what is implicit normalization? 1 point m. Okay, 1 point m. 1 point m. Now, these are the denormalized value. Okay. These are the denormalized value, like minus 1 power s into 1 point m into 2 power minus 126, because in a single precision we can only do up to this number minus, we can only store till this much number. Okay, this is the range, this is the range. And for double precision we can store till minus 1022. Okay, minus 1022. Okay, so these are the denormalized. And now this is the very important table. This is the very important table. Okay, again very important. Just remember each and every points. Okay, so now here these are the these values are reserved for, these values are reserved. Okay, so that is called as reserved quantity. So if you want to represent positive 0, then sign is all 0, exponent all 0, mantis all 0, because it is plus. If you want to represent negative 0, so just you have to change the sign bit. Okay, and each and everything will be 0. Now if you want to represent positive infinity, sign will be 0, exponent will be all ones, mantissa will be all zeros. Okay, if you want to represent minus infinity, just you have to change the sign. Okay, 0 to 1, and then exponent all ones, mantissa all zeros. Then if you want to represent not a number, okay, not a number, it's like invalid or indeterminate number. So sign can be 0 or 1, anything. Exponent should be all 1. Mantissa can be any non-zero. Okay, any non-zero, any non-zero. Now if you want to represent denormalized number, denormalized means very small magnitude. See, just you have to change here. Instead of all ones, you have to just represent exponent with the all zeros, and each and everything is same as the format of not a number. Okay, not a number. Like Mentisa should be any non-zero sign can be 0 or 1. Okay, sign can be 0 or 1. Now this is our case like IEEE. Okay, IEEE 754. This is our case like normalized number, which is implicit normalized. Okay, which is implicit normalized. So a sign can be 0 or 1. Exponent should not be all zeros and all ones, right? Why? Because see here, all zeros and all ones are reserved. Okay, all ones and all zeros are reserved. And Mentisa can be any value. Okay, Mentisa can be any value. So this the table which is very much important in the gate PYQs. Also many questions are coming in with this table. Okay, with this table. So now we go to the next chapter and we'll see cache organization, each and every important formulas. Okay, each and every important formulas. Now this is the cache organization. So first is block size of cache and main memory are same. Okay, block size of cache and main memory are same. Now how to find total number of blocks? How to find total number of blocks? Number of blocks in the cache memory is size of cache. You take size of cache, you just divide by block size. Okay, you just divide it by block size. Then you will get total number of blocks in the cache memory. Okay, then you will get total number of blocks in the cache memory. Now next uh, formula is if main memory address is given in decimal. Okay, in decimal if it is given, how to find the block number? Okay, if main memory address is given, how to find the main memory block number? So that will be flow of address, you do address divided by block size. Okay, divided by block size. Okay, and we have see in the formulas. I am not explaining each and everything in a detail because we have seen it many times in the lectures, in the short notes, and then in the formula. It's not required. Okay, so if you want to see, then go to the course and watch my each and every lectures. I have explained each and everything in a very detail. Now next one is cache controller stores. Okay, so what the cache controller will store? It will store the tag directory size. Okay, tag directory size for all the mappings. And what is the tag directory size? It is which is equal to total number of blocks in the cache into tag plus extra bits. Okay, tag plus extra bits. So it's mainly used for tag directory, right? Because that's why it is called as tag directory. So it stores tag information plus extra bits, and extra bit maybe can be a valid bit, can be dirty bit, or that will be given in the question. Okay, and if nothing is given, you can take 0. Okay, you can take 0. If nothing is given, you can take 0. Now these are the three formulas which are used. Okay, many times. So what is the cache memory block number? In this is the case for diag mapping. Okay, diag mapping. So cache memory block number, how you can find? What you have to do? Main memory block number you have to take modulo you have to do with total number of blocks. Okay, total number of blocks in the cache memory. Total number of blocks in the cache memory. Now next is how you can find the cache memory set number. So this is for set associative. This is for set associative. How you can find cache memory set number? So you take main memory block number. You do modulo with total number of sets. Okay, total number of sets. You do with total number of sets. Now, next is total number of sets in the cache memory. How you can find it? So first you take total number of block divided by associativity. So example, let's say you have 8-way. Okay, 8-way associative. What does it mean? One set contain 8 lines. Okay, 8 lines. One set contains 8 lines. So if you have here total number of blocks, okay, total number of blocks, what you can do? What you can do? How to find total number of sets? Can you do you can simply do number of blocks divided by associativity, right? This is the associativity. So that's the formula. Okay, that's the formula. Got it? Uh, Now we'll see each and both the mappings. Okay, like we will see all the three mappings. So this is the mapping formula for diag associativity, is also called as one-way set associative. So this is the mapping formula. This is the main memory address. Okay, this is the main memory address. Now you look here, what I have given here. See, main memory address is given in decimal, then block number is you have to divide by block size. So here this is the byte offset. Okay, this is the byte offset. That is the block size only. Right? That is the block size only. Because if block size is, let's say, 256 byte, okay, what is the byte offset? So it will be 8 bits. Okay, 8 bits. So you divide by block size, then what you will get here, this is the block number. Okay, main memory block number, main memory block number. Now look here, what I told, how to find cache memory block number, main memory block number modulo total number of blocks. Okay, so see here, what we are doing, cache memory block number we are picking. Okay, and main memory block number we just do modulo. Okay, we and you know it that whenever we do modulo, then lsb bits we are getting, right? Lsb bits we are getting. So here you will get cache memory block number. Okay, cache memory block number, and then main memory block number is divided into two, like tag into tag and cache memory block number. Okay, so now see this here, this term is also cache size. Okay, so from here to here, why? Because this particular cache memory block number will represent total number of blocks. Okay, will represent total blocks in cache. Okay, total blocks in cache memory into, can I do byte offset means block size, so can I do multiply directly? Okay, can I multiply directly, so I will get cache size, right? I will get cache size. So that is the thing. Okay, so here you can infer two three things. Okay, you can infer two three things, so remember that. Okay, remember that. Now set associative. Okay, set associative, so that is KV. And what is the difference here? Instead of cache memory block number, we are writing here set offset, right? So set offset means cache memory set number. Okay, cache memory set number, and each and everything will be same. Okay, each and everything will be same, like here we tag, and here that is byte offset. Okay, byte offset or block size. Okay, block size. Okay, so now uh yeah, so this is the one important result. Okay, one important, it's like not a result, but it's like one important concept. So here, if you increase the associativity, okay, if you increase the associativity, so what can happen? Okay, I will not go into that much detail. Okay, I will not go, because I have explained this many a times in my lecture, in my short notes, everywhere. Okay, so please watch them if you want to learn in a more detail. So this is the this is the concept where if you go this way. Okay, if you go this way, what does it mean? If you increasing the associativity, okay, so let's say if you are here, okay, and then if you increase the associativity, what will happen? You will shift this bit. Okay, shifting this bit means now your this particular term will be shortened in size. Okay, so previously, let's say it requires 16 bit. Okay, now it will requires 13 bit. Okay, example. So now where this extra 3 bits will go, 3 bits will be goes to the tag, right? Goes to the tag. Okay, so see here, tag will increase if you increase the associativity. Okay, if you increase the associativity. So this is one concept. Okay, this is one concept, because there is a proof also. But if I show this proof here, then this class will go too long. Okay, but that is not required. Okay, in because in this lecture itself only I have told you what you have to do before coming to this lecture. Okay? Now look here, if associativity is doubled. Okay, if associativity is doubled, what can happen? Set number, right? Set number reduces by 1 and tag increases by 1, right? So it maintains the equilibrium. It maintains the equilibrium, like something is increasing, something is decreasing, so we are maintaining it, right? We are maintaining the equilibrium. Like if you increase the associativity from 8 way to double. Okay, you are doubling, like 16 way. Okay, you do double, then what will happen? One bit shift will happen. Okay, so currently this s index bit is taking, let's say, 16. Okay, now it will take, okay, one bit change. Okay, so now it will take 15. Okay, now it will take 15. So where this one extra bit will go? It will go to the tag. Okay, so previously, let's say your tag is, let's say, 17 bits. Okay, 17 bits. Now here in this case, what it will, your tag will be 18 bits. Okay, so this is the just a example. Okay, just example. So that is the thing. Now this is the important formula. If cache memory size is given, log like associativity is given. Okay, so this particular formula comes. Okay, this formula comes if you understand this particular logic in a very detail. So tag will be main memory address minus log of cache memory size minus log k. Okay, so some hint I want to give. So in if you in a direct way, in a direct associative, if this is your entire cache size, right? Entire cache size. But now in the set associative, what we are doing? Here comes the extra term like KV associative comes, KV associative. Got it? So what you are doing? Because of this KV, okay, this is one way, right? This is one way. This is one way. And this is KV. Okay, this is one way and this is KV. So what we have done? We have to shift this bit, right? We have to shift this bit, like we have to shift this bit somewhere here, right? So that's why your cache size will decrease. Okay, your cache size will decrease. So see here, your cache size will now decrease, like log cache size minus log 2, like log base 2k. Okay, log base 2k. And here in case of in case of one way, what is the tag will be memory address, main memory address minus, can I add this log of cache size, can I add this log of cache size, right? This entire term, because this entire term is cache size. So I can do directly log, right? I can take directly log. Now because of this associativity, because of this kva, I have to subtract with minus of log base 2k. Okay, log base 2k. Got it? Okay, so now this is the fully associative. Okay, now next last one is fully associative. Okay, last one is fully associative. So in a fully associative, tag is the main memory block number. Okay, so here this is the main memory address. Okay, and this is same as main memory block number. Okay, and there are two fields only. There are two fields only, tag and byte offset. Okay, there are two fields, tag and byte offset. So these are the mapping formulas for the cache, right? There are three mapping, like direct mapping, set associative mapping, and fully associative mapping. Okay. Now we look into important details about average memory access formula. Okay, average memory access time. So average memory access time. So what is the average memory access time? Okay, so here before that, first of all, what is the hit time? So time seen by CPU when cache hit occurs. Okay, so whatever time seen by CPU, that is called as hit time, and also it is also called as cache memory access time. Okay, so see, that is when item is in cache. Okay, when item is in cache, then total delay or time or latency which is seen by CPU to access it. Okay, because it is present in the cache, so you have to access. That's called as hit time, and cache hit time is same as cache memory access time. Okay, cache memory access time. Now, what is the formula for hit ratio, hit rate, or H? Okay, you can simply call it as H. That will be total hits divided by total accesses, right? Total hits divided by total accesses. Now, what is the miss ratio? Miss ratio means total misses divided by total accesses, and that can be written also as 1 minus H, right? 1 minus H. 1 minus H. Okay. Now, what is the formula for miss penalty and miss time? Okay. So miss penalty means time required to fetch the block from memory hierarchy from lower level plus time to deliver this block to the processor. Okay. So this is the miss penalty time. First of all, you are transferring because miss happens. Okay. Because miss happens. Miss means something is not present in the cache, right? What is the miss? Miss means item is not present, item is not present. So you fetch the block, and then you deliver the block. Okay. You fetch the block and then you deliver the block to the processor. So entire time is called as miss penalty time. Okay. Now, what is the miss time? So total time spent processing the miss. Okay. Total time spent processing the miss. So miss time is having two quantity, miss penalty plus hit time. Okay. Miss penalty plus hit time. So why hit time? Why hit time? Hit time is also called as excess time, right? Is also called as excess time. So how we can get to know that whether hit happens or miss happens? Tell me. How we can get to know whether hit happens or miss happens? So we first have access the cache, right? We have first access the cache, then only we get to know. So that's why we have to add access time. Okay, that's why we have to add access time, and then we get to know that miss happens. Okay, miss happens. So we have to process that miss, right? So we have to process the miss. We have to fetch the block. We have to deliver the block. So that is your miss penalty. Okay, that is your miss penalty. Okay, so there are two terms involved here. There are two terms involved here. So please take care of this. Please take care of this. Many students, I have seen that they are confusing in this particular things, but please take care. Okay. So now, proceeding further, so this is the basic average memory access time formula. Okay, this is the most important. So hit time plus miss rate into miss penalty. Okay, you can also write like this way. So average memory access time is same as hit ratio into hit time. Okay, into hit time plus miss ratio. Okay, plus miss ratio into miss time. Okay, into miss time, and miss time having two quantity like miss penalty plus hit time. So here what I can do, I can take hit time common, I can take hit time common. So I have take hit time common. What is left? Miss ratio into miss penalty, right? So this is the simplified formula. Okay, this is the simplified formula. You can use anyone. Okay, you can use anyone, but that is the simplified formula. Okay. Now this is the important note. Okay, important note. So the formula we have, the definition we have already seen this miss penalty. Now see, majority of resource defines miss penalty as additional time. Okay, additional time for access in a case of miss, not including time to check the cache. Okay, not including. See, not including time to check the cache. So that's why we are adding this extra time, which is hit time. Okay, extra time which is hit time. But if in a question if they have explicitly mentioned in a question explicitly mentioned about miss penalty, it includes time to check the cache. Okay, time to check the cache, then your miss time is same as miss penalty, right? Why? Because it internally, okay, it miss penalty internally includes this time. Okay, internally includes for checking the time, right? Checking the cache time, that is implicitly include. Got it or not? Yes or no? Tell me. Right. So this is the important note I want to deliver. Okay. So that's why I put here. So please take care what is given in the question, what is not given in the question. Okay. Sometimes see what happens that you have to also check the options. Okay. Let's say some your answer is not matching if you are using this formula, then you can quickly do with this formula. Okay. Because many a time some confusion is happening in this type of questions, but you can quickly do it by checking the options. Okay, checking the options. Okay, now let's say we have two levels of cache. Okay, what is the average memory access time for two level of cache? So if this is the CPU, this is the level 1, this is the level 2, this is the main memory. Okay, main memory. Now this is the formula. Okay, this is the formula, how it have come. Okay, how it come. So please see here, I have zoomed this picture. Okay, so CPU generates the memory request. Okay, CPU generates the memory request. So first of all, here we go to the L1, right? We go to the L1. So here in the L1, either hit happens or miss happens. So L1 hit. Okay. So if hit happens, then you have to include L1 hit time, right? L1 hit time or hit time as access time. So let's say that is TL1. Okay, let's say that is TL1. Now let's say miss happens. Okay, let's say miss happens. So if L1 miss happens, we go to the L2. We go to the L2. So in the L2, either hit happens or miss happens. Okay. So if hit happens, if in a L2 if hit happens, so L2 access time we have to add, right? Hit time. Okay, hit time or access time we have to add. But how we get to know that whether L2 hit happens or miss happens? We have checked L1 at first. We have checked L1. So we have to add it explicitly. Okay, we have to add it explicitly. TL1 at access time. Now, let's say miss happens. Okay, let's say miss happens. So if miss happens, okay, if miss happens, we go to the memory, and then we can get. So that is the T memory time, T main memory. But how we can get to know? How we can get to know whether here miss? So we first come to L1, then we come to the L2, and then we go to the main memory, right? In case of miss. So this is the diagram you have to always make. If you have any confusion, then you always have to make this diagram. Then everything will be simple. Okay, then everything will be simple. See, now first, if you do this diagram, you have to follow each and every path. Okay, so here one path, here another path, and here another path. Okay, so there are three paths: first, second, and third. Okay, so there are three paths. So in the first path, see L1 hit rate. So this is the L1 hit rate into TL1 into TL1. Now see the second path. L1 missed, so L1 missed, then L2 hit it, L2 hit it, then this particular quantity, right? Then look into third path. So L1 missed, okay, this is the L1 missed, then L2 missed, this is the L2 missed, this entire term, okay, this entire term. So this very simple way, very simple way. You don't have to remember anything if you have followed this particular. But if you made this particular diagram, you don't have to mug up anything. And then once you simplify this formula, once you simplify this formula, you will get this term. Okay, you get this simplified term. You get this simplified term. Okay, you get this simplified term. Okay, so now we are proceeding further. So average memory access time is over. Okay, average memory access time is over. So here let's say one important formula. So here let's say if number of read and write instructions are given, okay, and different hit misses are there. So different hit or misses for a read, different read and misses for write. Then so that is given. So how you have to find average memory access formula? Percentage of read, how many times read happens, into you have to find T average separately for read plus percentage of write into you have to separately write T average, you have to separately derive average formula for write. Okay, average formula for write, like average memory access formula. Okay, yeah. So now this is not a formula. Okay, this is not a formula, it's a concept, but because it's very important. Okay, and many PYQs are there, that's why I mentioned here. Okay, that's why I mentioned here. So if you are doing right, then your cache is divided into four types. Okay, four types. Like if you got a hit, then your cache is divided into either write through cache or write back cache. If you get write miss, okay, write miss, okay, and it is write hit, okay, then your cache is divided into two types. This is one time, which is also called as write allocate, and no write allocate. Okay, no write allocate, no write allocate. Now, what the write allocate says, it says that bring the data from memory to cache. What the no write allocate said, no bringing of data. Okay, directly update memory. Okay, main memory. Directly update main memory. You don't have to bring the data to the cache. Okay, you don't have to bring. You no need to bring the data to the cache. Okay, directly update it. Directly update it. So definitions, I am not going in that much detail. Okay, because it's a formula class, it's not a class for explaining each and everything. Okay, because I hope that you know each and every definition. So remember this combination, like write through with no write allocate, write back plus no write allocate, plus write allocate. Okay, directly PYQs are there, direct PYQs. Okay, direct PYQs are there. Okay, now now proceeding further with the local miss and global miss. So what is the global miss? So here these also PYQs are coming. Okay. So the some necessary things only I have put into the formula. Okay, formula sheet, which you may require. Okay. So local miss means how you can find the local miss rate. So misses in this cache divided by excesses to this cache. Okay. So if you want to find example, let's say if you want to find L1, L2. Okay. Let's say L2 local miss. What you have to find? L2 misses. Okay. L2 misses divided by L2 access. Okay, how many accesses L2 got? Okay, L2 accesses divided by so L2 means divided by L2 access. Okay, if you want to find L1 local, okay, L1 local, so L1 means divided by L1 access. Okay, L1 access. So yeah, this is the local means. Okay, this is the local means. There is nothing much in the local means, but you just have to take care that misses is miss only, but accesses will be locally. Okay, locally access you have to take, local access you have to take. Okay, local access. Now if you look global miss, what is the global miss set? Misses in this case, okay, this is the same term, numerator is same term, but in the denominator, total memory efficiency by CPU. Okay, so globally you see how many CPU have given accesses. Okay, how many CPU have asked the request. Okay, CPU, how many CPU made the request. Okay, So here you see locally, here you see globally. Got it? So that's all about local means and global means. Got it? Okay, so we have seen, I think, yeah, everything in the cache. Okay, we have seen everything in the cache chapter. Okay, we have seen everything in the cache chapter. Okay, so now we'll see pipelining. Okay, we will see now pipelining. So see in a pipelining, there are not much, there are not much formulas because there are many concepts. Okay, there are many concepts. I think this much only required. Okay, this much only is required because um, many important concepts and everything I have put in the short notes. Okay, many important things I have put in the short notes. But this much formula is only present. So what is the pipeline time for n instruction? Okay, pipeline time for n instruction. So if you have k stages, if you have k stages and n instructions, okay, k stages and n instructions. So how you can find? So first instruction, one instruction will take first instruction will take k cycle, right? K cycle. So k cycle, your first instruction will take k cycle plus rest of the n minus 1 will take 1 cycle. Okay, so this will be your total cycles. Okay, total cycles into cycle time, right? So TP is your pipeline cycle time. Pipeline cycle time. Okay, TP is your pipeline cycle time. So that is the pipeline time for n instruction. Okay, this is the entire formula. Okay, this is the formula. Now what is the non-pipeline time? What is the non-pipeline time? Non-pipeline time. So it's simple, right? So if you have n instruction, n into non-pipeline cycle time. Okay, n into non-pipeline cycle time, because here in the case of non-pipeline, each and every instruction will take non-cycle time, right? Non-cycle time. Now if you want to find the speed up, okay, if you want to find speed up, so speed up will be speed up of, okay, so here let me put it correctly. So speed up of pipeline over non-pipeline. Okay, so if you want to find speed up of pipeline over non-pipeline, so what you have to do, whatever speed up you have to find, you have to add in a denominator. Okay, so that's why in a denominator we have your pipeline time, right? Because we are asking pipeline, and whichever we are comparing, that you have to add in numerator. Okay, so see the numerator. Okay, so in the numerator we have add non-cycle time, right? Non-cycle time. So this is the important thing. Okay, this is the important thing because in the gate exam they may take with this particular like wordings, with the wording, with the definition they can take. Okay, now what is the ideal speed up? What is the ideal speed up? Take n to be infinity. Okay, let's say n to be infinity, so you can remove those both the terms, like n and this. Okay, this is also n infinity, so minus 1 and k plus k and minus 1 doesn't matter, right? Because it's infinite. So that will be tn divided by tp. Yes, tn divided by tp. Okay, now let's say if now next next both the formulas are, let's say if your stages, okay, if your stages have different delays. Okay, if different delays, like let's say 3 nanosecond, 2 nanosecond, 1 nanosecond. Okay, let's say 6 nanosecond, and your stages have inter buffer delay. Okay, inter buffer, you have this intermediate buffer. Okay, let's say this is 2 nanosecond. Okay, each and every one is 2 nanosecond. So what is the TP? What is the TP for it? You have to do maximum of segment delay. You have to do maximum of segment. So what is the answer? What is the maximum of 3216? That is 6 plus register delay. Okay, plus so 2. So in total 8 nanosecond. Right? In total 8 nanosecond. Now what is the TN? How to find TN? Non-cycle, non-pipeline cycle time. Non-pipeline cycle time. You have to add sum of all segment delay. Okay, so 3 plus 2 plus 1 plus 6. So 5 plus 1, 6, 6 plus 6, 12 nanosecond. Okay. So Tn will be your 12 nanosecond. Got it? Now, next important formula is throughput. Okay. Next important formula is throughput. So first of all, what the throughput is? Throughput of pipeline means, throughput says that instruction executed per second, right? Instruction executed per second. So let's say in a k plus n minus 1 into tp time, okay, we have executed n instruction, okay, n instruction. So in a 1 second, how many instructions, okay, how many instructions? So n divided by k plus n minus 1 into tp, okay, into tp. Now take n to be very large, right? Let's say n to be very large, let's say infinity. So we can remove this term. So that will be same as 1 divided by tp, right? 1 divided by tp. So that's what directly written here. Okay, throughput of pipeline is 1 divided by TP. Okay. So if you forgot, then you can derive it. Okay. If you forgot, you can derive it the simple, like in the simple manner. Okay, in the simple manner. Now, what is the CPI average? Okay. So this is one ideal CPI. Okay. Ideal CPI is one. Okay. Ideal CPI. So CPI means cycle per instruction, right? CPI means cycle per instruction. So your ideal CPI is one. So ideal CPI is one. But you have some stalls and all, right? Your stalls and all in a pipeline. So one plus stall frequency into stall cycle, right? One plus extra cycles we are adding. One plus extra cycles. Yes or no? So that is this thing, right? Extra cycles. One plus extra cycles. Now, next point is one instruction execution time. Okay, what is the one instruction execution time? So in average, okay, average, what is one instruction execution time? So CPI average into cycle time, yes or no? CPI means cycle per instruction. So per instruction, this term will give me per instruction how much cycle it will take into cycle time. So I can write one instruction total time, right? One instruction time. CPI into TP. Got it or not? CPI into TP. Yes. Now next last formula is stalls because of bands. Okay, because of bands, how many stalls you will get? So if in a ith stage condition is evaluated, okay, if in a ith stage condition is evaluated, how many stalls you will get? I minus one, right? I minus one. I minus one. Okay. So yeah, so this is all about the pipelining. Okay, this is the all about pipelining. Yeah, I think not much formulas are required. Yeah, one thing is that, okay, one thing, let's say maybe I can write it. Okay, maybe you can add it. So only row dependencies create hazards. Okay, can only create hazards. And how to only this dependency. Okay, so how to get to know? So run the normal pipelining. Okay, run or do normal do normal pipeline. Okay, and check if problem is there or not. Okay, if problem is there or not, is there or not. So row dependency, it may or may not create stalls, right? May or may not create stall, may or may not. Okay, so how to get to know that whether they have created stalls or not? Okay, how to get to know whether they have created? You have to do this: perform normal pipeline and check if some problem is there or not. Okay, check some if problem is there or not. Problem is there or not means you have to check whether it is taking extra cycles or not, right? Because extra cycle means stall, extra cycle means stall, and whichever like conditions which create stalls, right? That is called as hazard. Okay, what is the hazard? Hazard means whichever condition which creates the stalls, that is called as hazards. Yes or no? So you have to check the problem is not means check stalls or extra cycles. Okay. Okay, so now we are done with pipelining. Okay, we are done with pipelining chapter. Now we'll see important formulas for CPU and control unit chapter. Okay, CPU and control unit. So what is the cycle time? Cycle time. What is the cycle time? So cycle time is same as 1 divided by clock rate. Like time is same as 1 divided by frequency, right? Clock rate is frequency. Got it? So this way you can find. Now one instruction execution time, we have seen this just now. Okay, we have seen just now this same formula. One instruction execution time is same as CPI into cycle time. Okay, let's say in a question. Okay, let's say in a question clock rate is given. Okay, clock rate is given. So what you can do, CPI divided by clock rate, right? So both the formulas have same. With the help of this, cycle time is 1 divided by clock rate, right? With the help of this, got it? So anything can be given, okay? Anything can be given. So take care that, take care what it is given, okay? Please check the question carefully. And what is the program execution time? Program execution time is, so program content, let's say n instruction, okay? So one instruction will take CPI into cycle time. So n instruction will take n into CPI into cycle time. Yes, just have to multiply this term with n, okay? N into same thing. Yeah? Now one important formula is this MAPS, okay? MAPS is million instruction, a million instruction per second, okay? Million instruction per second. So this is the formula, like clock rate divided by CPU into 10 power 6, right? Because million is 10 power 6, million is 10 power 6, right? 1 million is 10 lakh, right? 1 million means 10 lakh, right? And 1 lakh means 10 power 5, 10 into 10 power 5, which is 10 power 6, okay? So that's what it written here, 10 power 6, got it? So yeah, this three four formulas is only present in the CPU. Okay, I think there is, for a CPU point of view, but in a control unit also, if we see, there are concepts only, like there are concepts about hardwired unit, then microprogram. In a microprogram, you have horizontal programming, right? Horizontal, then you have vertical. I think there in that there are no formula is there, right? But there are questions present, but that can be solved only when you have grasped in the concepts, right? When you have very good know the concept, then only. But there is no formula. That's why I have not written. I think one particular formula is there in the control unit. That's not a formula, but there is a format. Okay, if this is the control word, okay, this is the control word. You have the control signals present here. Control signals. Okay, control signals, and here you have mux. Okay, you have mux, and then you have next address, right? Next address. Yeah, so this is the one particular format which is there. I think there is no much formula is there. Okay, there are many concepts, right? There are many concepts, but they are not formulas. Okay, in the control unit chapter, basically. So that's why I haven't put it. Okay, I haven't put it. If you have found it, you can write it. Okay, you can write in your formula notes. Okay, you can add in your formula notes if you want to add anything explicitly. Got it? Yeah. So now we are done with all the thing. It's like only the last chapter. Okay, we are left with just last chapter. So last chapter is all about DMA and interrupts, right? In DMA, interrupts, and IO. Okay, IO. So in the IO, you have three methods. Like first is programmed IO, which is also called as polling. Then interrupt driven IO, and then you have DMA. Okay, then you have DMA. So you have three methods here. Now in the polling, total time. Okay, what is the total time take? Total time will be time to check the status, right? Time to check whether a device is ready or not, right? Whether a device is ready or not, device is ready or not, stuff like that, right? So that's why it is time to check the status plus time to transfer data. Okay, because once the device is ready, right? Device ready, you have to transfer it, right? You have to transfer it. So we keeps on poll it, like CPU keeps on poll it, whether IO is ready, whether IO is ready, and if it is ready, it can transfer it. Okay, so time to transfer data. So that is the total time. Okay? That is the total time taken. Now, in case of interrupt driven IO, what is the total time taken? What is the total time taken? That will be interrupt overhead, right? What is the interrupt overhead? Like you are saving the context, right? Saves the context. You are saving the context. Then you are doing like performing ISI, right? Perform ISI. Okay. Then you restore the context. Okay, restore context. All these things, this will take interrupt overhead will take plus time to service interrupt. Okay, plus time to service the interrupt. Okay, so this is the total time taken. Okay, that is the total time taken. Now in DMA, first, and this important formula is, okay, this very important. In with just this formula, many PYQs are there. Okay, 3 4 PYQs are there in the recent years. So what is the maximum data transferred without CPU intervention? Okay, what is the maximum data transfer? So in a one go, okay, in one go, how many maximum data is transferred? Okay, so if X is the number of bits in the data count register, okay, so if the X is number of bits in the data count register, so 2 power X minus 1 data can be transferred in a one go, okay, in one go. In one go, 2 power X minus 1 data will be transferred. Got it? Now you have different like based on okay. Now DMA have different modes. Okay, DMA have direct memory access. Okay, DMA means direct memory access. So it has different modes like burst mode, cycle stealing mode, interleaving mode. Okay, so why they have modes? So how it will take the buses? Okay, how it takes the how it will get how it will get excess of buses, excess of CPU buses, okay, CPU buses. So with that, okay, so based on this particular thing, that how it will get excess of CPU buses, there are three modes: burst mode, cycle stealing, and interleaving. Now in the burst mode, burst amount of data is transferred. Okay, in the burst mode, burst amount of data is transferred. So percentage of time CPU is blocked is transfer time to memory. Okay, transfer time divided by preparation time plus transfer time. Okay, preparation time plus transfer time. Okay, so here I am writing burst amount of data is transferred. Okay, is transferred. Burst amount of data, or you can say one entire block. Okay, block of data. Okay, block of data is transferred. Okay, block of data is transferred. So block having burst amount at, so block of data is transferred. Now we are in the cycle stealing. What you are doing, one byte is transferred at, one byte is transferred in one cycle. Okay, in one cycle. So in one cycle, one byte is transferred. Okay, one byte is transferred. So percentage of CPU block will be how much time CPU will block? Transfer time divided by preparation time only we have to add, okay, into 100, okay, into 100%. Got it? So this much time CPU will be blocked, okay, this much time CPU will be blocked. Now, the last mode, interleaving mode, which means here, no waiting or blocking, okay. So here, CPU won't wait or block, okay, CPU will not wait or block. So here I am adding when CPU doesn't require, when CPU doesn't need buses, then it gives to DMA. Okay, it gives to DMA. It gives to DMA. So here if here in this case, okay, because if CPU doesn't require the buses, it gives to DMA. So no waiting, so no CPU waiting or no blocking. Got it? No CPU waiting or blocking. Got it or not? Tell me, got it or not? Right. So with that, all the chapters are over. We have seen DMA, we have seen CPU and cycle time. We have seen pipelining, we have seen cache organization formulas, right? Then we have seen floating point representation. We have seen disk. We have seen risk versus risk. We have seen addressing modes and instructions. We have seen memory organization. Okay. So uh, with that entire COA formula sheet is done. Okay. We have looked into very important formulas. Okay, important formulas which is required. Got it? So with that, entire formula is over. Okay, entire formula is done. So thanks for joining. Thanks for watching. And if you have any doubt, let me know. And thanks for joining. Okay, and yeah, thanks for joining. Thanks for joining. We'll meet you in the next one. Okay, thanks for joining.